Hello everyone, I'm Xinkuan from Chinese Academy of Science, and I'm here to present our work. Shape-biased CNNs are not always superior in out-of-distribution robustness. First, let's talk about the motivation. There are some consensus in the community of model robustness. Loads of work have shown that human vision system is shape-biased, and shape-biased model tends to have higher robustness. For us, however, we believe that there are special cases that are not favored by shape-biased models. Case 1 is from the perspective of categories. Especially, we start with the two most generic categories in the world, animals and artifacts. We hypothesize that shape information is less discriminative to distinguish animals. As shown in the figure below, using shape information to distinguish horse and zebra is difficult, and the invariant feature for the cat is texture information. These daily observations are also backed up by research in the field of cognitive science and psychology. Case 2 is from the perspective of o.o.d scenarios. The statement that shape-biased model favors corruption shift is, in general, doesn't imply that it favors every o.o.d type. Especially, we hypothesize that shape information is less reliable for corruption scenarios like elastic transformation and blur. We validate our hypothesis on case 1 first. Since we focus on animal and artifact categories, we build up the category-balanced ImageNet to ensure equal representation of animal and artifacts in the dataset. It is an ImageNet subset with 64 animal and 64 artifact categories. Also, animal and artifact categories have similar hierarchical structure and image numbers. To investigate whether shape or texture information are more discriminative, we train and test on shape or texture features only. Shape features include self-information map and canny edge extraction. Texture features include patch permutation with scales of 4, 8, and 16. While for o.o.d testing, we use corrupted shape or texture features. The corruption method is the same as those to generate ImageNet corruption dataset. As for the result, we see clearly that shape information is more discriminative for artifacts than animals, while texture information is more discriminative for animals than artifacts. We then validate our hypothesis in case 2. To investigate whether shape-biased model always superior in various o.o.d scenarios, we choose 15 different corruptions in ImageNet corruption datasets. We train two models that are shape and texture biased respectively. The shape-biased model is trained with each image having 50% chance replaced by shape features. The texture-biased model is trained on the same dataset with each image having 50% chance replaced by texture features. Both models are evaluated on the corrupted test set. The results on all 15 natural corruption o.o.d scenarios are shown in the table. The shape-biased model performs better in general as expected, while for all types of blurs and elastic transformation, the texture-biased model shows clear higher robustness. This observation can be explained by the fact that when images are blurred or subjected to elastic transformation, their shape information changes more than texture, leaving their texture information as a more predictive cue. Therefore, although the shape-biased model has higher average accuracy, the text-biased model shows noticeable advantage in certain scenarios where shape information is less reliable. According to the validation experiment, relying on fixed decision rule coupled with uniform feature extractions would be insufficient in maintaining reliability against distribution shifts. Therefore, we designed a novel model named Shape-Texture Adaptive Recombination (STAR) with dynamic decision rules to enhance performance across a spectrum of o.o.d scenarios. The overall framework of the proposed method is visualized in this figure. We first pre-train a debiased backbone and 3 heads that specialize in extracting robust shape, texture, and debiased features respectively. Then a recombination head is trained to adaptively regulate the contribution of these distinctive features in accordance with individual instance. Compared to standard models, STAR incorporates additional parameters through 3 additional heads and introduces an additional training overheads of 20 epochs for the recombination head. In training stage 1, the 3 specialized heads are trained using augmix method with distinct augmentation pools. For example, the shape-based head is trained by original images and images augmented by the texture changing pool exclusively, using cross-entropy classification laws and GS divergence consistent laws as in augmix. The total loss is shown in equation 2. The texture changing pool contains color channel operations including solarize, equalize, auto-contrast, and posterize, which do not affect spatial information and forces the model to learn robust shape features. The shape changing pool contains spatial operations including translate, shear, and rotate, which cause more changes in shape information than texture and force the model to learn robust texture features. And the debiased pool is a combination of operations of both shape and texture changing pool. In training stage 2, the recombination head HR is designed to adaptively adjust the contributions of these distinctive features in accordance with each instance. Notably, images and augmented images are fed into all heads, resulting in extracted features HSFI, HTFI, and HDFI. The recombination head outputs 3 values as in equation 3, and the final prediction is a convex combination of the predictions from the specialized heads with weights from the recombination head. The classification results Y and training objective L for image X can be calculated as in equation 4 and 5. For ImageNet experiment, we exploit 128 categories in category-balanced ImageNet for model training, and utilize data that shares the same categories as the training set exclusively for the test as mentioned below. ImageNet C and ImageNet C-bar dataset are used to evaluate o.o.d robustness to corruption. Fast gradient descent method is used to evaluate o.o.d robustness to adversarial attacks. ImageNet R dataset and ImageNet Sketch dataset are used to evaluate o.o.d robustness to style shift. ImageNet V2 dataset is used to evaluate o.o.d robustness to dataset shift. Here is the result. We can see that STAR achieves the highest overall o.o.d robustness and consistently enhance performance across all individual o.o.d scenarios. Similar experiments on CIFAR 10 and Office Home with various architectures illustrate the generalization of STAR. Finally, the conclusion. In this work, we dive deeper into the intricate relationship between shape and texture information and o.o.d robustness. We find that shape information is not always superior in distinct categories, and shape-based model is not always superior across various o.o.d scenarios. Based on these observations, we proposed Shape-Texture Adaptive Recombination to adaptively adjust the contributions of shape, texture, and debiased features across different instances. The superior performance of multiple datasets under diverse o.o.d scenarios, including image corruption, adversarial attacks, style shift, and dataset shift, proves the effectiveness and generalization of our proposed method. And that's all. Thanks for listening.